Hello and welcome to this class on wild or wheel impact load detector. This is being presented to you on IRMI's digital learning platform. So the purpose of wild is to protect the rail infrastructure and avoid derailments and accidents. And it achieves this objective by detecting defective wheels. So now what happens is a wheel is supposed to be perfectly circular like this, and it's supposed to rotate like this. This is the rail. Now what happens is that when we apply brakes by using the brake block, there is a great deal of friction acting on this wheel, and as a result of this, what happens is that over a period of time, if there is brake binding, what I mean by brake binding is that this brake applies to this wheel, and the wheel, instead of rotating, it starts to slide. There is no rotation in it anymore. The wheel braking force is so hard that the rotation stops and it starts to slide. So what happens in this case is that this brake block remains fixed and the wheel moves against it, and like you would run a chucky or a grinder, what happens is that over a period of time this material gets worked out. Okay, and the net result of it is that the wheel tends to attain a shape like this. It's no longer circular, it's become flat, and this situation is called a wheel flat. Okay. So what causes a wheel flat? Well, it's caused by brake binding. So what would happen if you have a wheel flat? Now if you have a wheel flat, what happens is that instead of moving smoothly on the rail surface, you have a hammering action. Like every time the wheel rotates afterwards, this part will come and hammer on the rails. And that hammering action is really bad for the rails and also for the rolling stock. There are some more situations which can lead to this dangerous situation. Let's suppose you have a broken spring. That will also result in uneven forces on the rails. And the result of these uneven forces is that over a period of time, your rail can become really damaged in a very bad way, and it can result in derailments and accidents. So the detection of defective wheels is extremely important. Okay, so this is just an example. Explanation of what I just explained now. Wheel is perfectly round, uniform load on the rail. When the wheel is flat, then you have a huge amount of load on the rail, and wheel impact load detector is used to catch this flatness in the early stage, and this protects your railway infrastructure. Okay, so how do we do that? The best way to do that is to have an instrumented track. That is, the track comes with strain gauges which are continuously monitoring the impact load, and so if the impact load is beyond a certain level, then it catches it. Then of course these strain gauges will catch some signals, and those of you who are experts in electronics, you would realize that this signal needs to be processed. It needs to be processed because there can be a lot of noise in it. Like when I take this lecture, it's possible that some of you are listening to music or talking to each other, and well, that's noise, and your brain needs to cut out that noise. So similarly, we need a signal conditioning unit to get rid of this noise. Then we have a real-time embedded controller. That's just a fancy name for a computational device which is going to log all these signals, and it is going to take these signals for further processing. And then you have a dedicated software. Here's where you have the intelligence, and what the software does is that it takes the signals from this controller, analyzes it with what should be the ideal pattern, and then realizes, okay, now there is a problem in this wheel, or well, this wheel is okay. Now why do we need this wireless data transfer? Well, these wheel impact detectors you would ideally like to put at a place where the trains are actually running at full speed, and that would be in the midsection. And now if you want somebody to keep going to the midsection to get this data, it's extremely difficult, and so you want to have a wireless data transfer facility. And of course, I just said that we are in the middle of nowhere. We are in the midsection picking up data. So in that sort of a place, the power supply situation is going to be really bad. So it's better to have a power backup. By the way, one of the wild installations that we had in Hubli was being powered by solar power. So that's the kind of innovations that we have to adopt to make sure that this technology works in a smooth manner. Okay, so what's the drop block diagram look like? So here's the TXR control room, that is the train examiner's control room. This is the site. You have a GSM model for transmitting the data. This is the rail, and here you can see L1, L6, L7, L8. So these are your strain gauges, the instrumented track or the strain gauges. So here you have a sensor which senses that the train is coming in. Here is a sensor which realizes that the train has gone out. So basically you need these exit and entry sensors to get the system into a state of readiness and to turn it off when it's not required. So these strain gauges, what they do, they cache this data, they send it to the signal conditioning modules. From here it goes to the real-time controller, and then it goes to the GSM module. Here we have a backup device for storing the data. This is the electricity board power or the primary power. This is the solar power or secondary power, which I was talking about. It doesn't consume much power, so it can be run on solar power also. And then of course, to operate all this, you need certain control systems. So that is the control and switching part. So this is a block diagram view of how a wheel impact load detector looks like. This is a short description. The tracks are provided with strain gauges, as I just mentioned, to measure the load pattern on the wheel. The track consists of 12 sleepers, which are the strain measuring zones. And this is the type of strain gauges that we use. And this rail length of 12 sleepers, how do we arrive at it? The way we arrive at it is that we want to capture 2 full rotations of a wheel on the rail. It's only when we capture the full rotation, we would know that there is a flat. Because if we don't capture the full rotation, it's possible that this is the wheel. Here there is a flat, and you might capture the rotation from here to here and miss out on this part and think that the wheel is perfectly okay. So that's why it's very important to capture the full rotation. So this is how you fix on it. This is generally fixed on a 60 kg rail. This is the distance between the sleepers. These are mostly technical details, so I'll just skip over this in this introductory class. This is how it looks in practice. Here you can see the strain gauges fitted on the track. These are the cables carrying the signal. Okay. So for those of you who are interested in the details, there is a concept called the Wheatstone bridge. Electrical engineers and electronic engineers would be very much aware of it. So the idea is that in a Wheatstone bridge, when these 4 resistances are balanced, then you don't get any reading here. You get a 0 reading here. But as the train moves, if these strains are not equal, then you get a deflection here. Okay, so these 8 strain gauges are connected to give a full bridge configuration. And in case there is an impact, then you would find that at that particular strain gauge, there will be a sudden increase in the strains recorded. That would cause this Wheatstone bridge to become unbalanced, and then the reading would no longer be 0. It would be a sharp increase in value, and that's what your software is looking for. So that's the basic principle and configuration of how a wheel impact load detector works. So this is just a photograph of an actual wheel impact load detector, just to give you a view of the system. This is how it looks. Okay, so this is basically the data acquisition unit. We said that there is a real-time embedded controller, right? So National Instruments, it's an American multinational company which makes this controller, and we make use of this controller to record the readings and further send them to the software for processing. So this is how a signal from an instrumented track looks like. Let's suppose this is a normal wheel, then you would find a graph like this. And if the wheel is defective, as I just said, you would find a peak like this. So this is the peak that we are looking at. And if you find this peak, then it means that there is something wrong with the wheel. So the beauty of Wild is that it's able to count the total number of axles. It's able to measure the average dynamic wheel load for each of the axles. It's able to determine the maximum dynamic wheel load, which is this peak that we are looking at. And it calculates an impact load factor, that is the ratio of this maximum dynamic wheel load and the average dynamic wheel load. And once you know this impact load factor, if it's greater than a certain extent, then it gives you an alarm signal. And if it's greater than a certain threshold value, then it gives a severe category alarm, in which case the coach actually has to be detached and examined. Also, because you have this entry and exit sensors, you are able to calculate the speed of each axle and the average speed of the train. And because you're continuously counting the axles, you're also able to find out that the exact position of the wheel in which you notice the defect. And this is related to the TXR control, and they can, further act on it and detach the coach or get it examined by the en route TXR staff. So thank you for listening. If you have any doubts, please ask them in the doubt sessions. Thank you.